Hi, we're going to look at this example where we're asked to evaluate a triple integral over this region. So the first thing that you always want to do in a problem like this is get a sketch of the region. It doesn't need to be a perfect graph of these surfaces, but a little sketch of that region would be helpful so you can think about whether the region is x simple, y simple, z simple, or if you want to switch to a different coordinate system. Okay, so first of all we have a cone, z equals the square root of x squared plus y squared. So that is the top half where z is greater than or equal to 0 only of the cone. Normally we might write that as z squared equals x squared plus y squared, but this is just the top half where z is the positive square root of x squared plus y squared. All right, and then the other surface it tells us is a paraboloid. If you think about the cross sections for that surface, when z equals 0, you have a circle in the xy plane. And then when either y or z is 0, you get parabolas with a vertex at z equals 6, and those parabolas open down. So just kind of a rough sketch of that surface. Looks sort of like that. And we want the region that is inside the cone and below the paraboloid. So I'm going to darken this in so we can focus on the correct region. So inside the cone and below the paraboloid. So I just kind of drew the outline of that, and the paraboloid meets the cone at some circle here. Those both have circular cross sections in the xy direction. So that part I darkened in, and I'll just color that in there so we can kind of focus. That's the region we want. Maybe it's helpful to erase the rest of the curves that we don't really need anymore. I'm just going to leave them on there though. Okay, so when you look at that region, you should notice that it is z simple, but it is not x or y simple. So you could set the integral up in x, y, z coordinates. However, this one actually works a lot nicer if you convert to cylindrical coordinates. These circular cross sections in the xy direction are what would indicate to you that it's probably helpful to convert this to cylindrical coordinates. Even if it didn't tell us to, that's an easier way to do this problem in general. Okay, so this region is z simple, so I'm going to do z on the inner integral. I need to convert my surfaces to z. So I have a paraboloid, z equals 6 minus x squared minus y squared. If I factor out the minus sign, then I can replace the x squared plus y squared with r squared. So I get z equals 6 minus r squared for the paraboloid. And then for the cone, I have z equals square root of x squared plus y squared. So I can replace the x squared plus y squared with r squared. And so I get z equals the square root of r squared, which is the absolute value of r, or plus or minus r. Since this is just the top half of the cone, we would just have the part where z is positive r, where both r and z are greater than or equal to 0. All right, so those are the equations of our surfaces converted to cylindrical coordinates. This region is z simple, so I'm just going to do ordinary z on the inner integral, and then essentially I'll just be using polar in the xy direction. So really we call that cylindrical coordinates when we're in 3 dimensions, but it's ordinary in the z direction and then polar in the xy direction. All right, so I'm just going to leave some space here for setting up my limits of integration. I'll do my inner integral first, as usual. So as we go through that region in the direction of increasing z, I enter at z equals r, and I leave at z equals 6 minus r squared. Now I want to go ahead and convert everything to r, theta, and z. Remember, those are our variables for cylindrical coordinates. So not just the limits of integration, but the function that I'm integrating as well. All right, so in polar coordinates, we know that x is r cosine theta. That's the same for cylindrical coordinates. And y is r sine theta, and z is just the same. And then remember, when you do polar coordinates, you have the extra r in your differential for polar coordinates. So the same thing in cylindrical coordinates, we've got an extra r as part of the differential, so that will end up being part of what I integrate. And then I did dz on the inner integral. So I'm going to go ahead and bracket that off, and then I'll set up my outer limits of integration in terms of r and theta. So to do those, I want to think about the projection of this region down into the xy plane, just the shadow of my solid down into the xy plane. So that's going to be a circle. I need to think a little bit about what that circle looks like. So I'm going to call that rxy, because we're in the xy plane, but I'm going to end up using polar coordinates for that. So there's the shadow of that region down in the xy plane, just on a little two-dimensional graph here. So I need to think about where the cone intersects the paraboloid to figure out how big this circle is here. So I could do that in either xy coordinates, or I'm going to go ahead and do it in cylindrical coordinates. So essentially we're just solving a system of equations where our two surfaces meet. That's an intersection, and I really would like to find the r value, not the z value here, although if I do find the z, that's okay. I could use that to find r. So I'm going to solve this system of equations really that come from our two surfaces here, z equals r and z equals 6 minus r squared. So I can substitute r into the second equation in place of z, and I get r equals 6 minus r squared. It's quadratic, so I can get all the variables on one side and then factor. That factors into r plus 3, r minus 2, and so I'll get r equals negative 3 and r equals 2. All right, r equals negative 3 is actually where, if I had a bottom part of that cone, where the bottom part of that cone would come down and meet the paraboloid. We don't really need that part, so that's not on the region we're interested in. We really just have r equals 2. So this circle here is radius 2. That's how wide this surface is where the cone intersects the paraboloid on the original picture. All right, so that's our r value. If I look at my two-dimensional picture here and think about going through that in the direction of increasing r, start at r equals 0 and I leave at r equals 2, and then my theta is just going to go 0 to 2 pi. So I'll go ahead and set up those limits of integration here. I'm going to do dr next, r equals 0 to 2, and d theta last. Theta is 0 to 2 pi. Those ones, it doesn't matter which order I really do those ones in. Okay, and then if I want to go ahead, if I just want to set it up, I could stop there. If I want to go ahead and evaluate it though, I need to think a little bit about this. And one thing to kind of pay attention to might actually be to look for some shortcuts. If I know that the integral maybe would be 0, or is just the area of a region or a volume of a region I know the volume of, I can just write that down. So actually on this problem there are some shortcuts that are helpful to look for. If you go back to the original integral and you kind of think about that, notice that that's a sum, and so you can really think about that original integral as the triple integral over the region d of x dv plus the triple integral over the region d of y dv plus the triple integral over the region d of z dv. And then if you look at your three-dimensional solid region and you think about all of these integrals as Riemann sums, you can see that two of these integrals actually will be 0. So if you notice that, then that helps, and you can kind of shortcut some of your work here to parts of it will 0 out. If you don't notice that, you just do the integration, and as long as you do everything correctly, those parts will 0 out anyway. But the two integrals that actually end up being 0 are the sum of all the x coordinates over that region, the first integral that I circled, and then the sum of all the y coordinates over that region. So if you just think about choosing points, putting them into the function, forming that Riemann sum, for every point in that region you're going to have a point with an x coordinate that's positive and an x coordinate that's negative, and those are going to exactly balance out when you look at the value of that function. So that part's just going to be 0. And then similarly, the triple integral over the region d, when you're adding up the y values, for every point on one side with a positive y coordinate, you'll have a corresponding point with a negative y coordinate, positive and negative y coordinates, and those two will add up to 0. So if you happen to notice that, then this one, you're going to evaluate that, And you should notice from looking at the region, on that region, those z coordinates are always greater than or equal to 0. So this part should be positive. All right, so if I kind of notice that, I can shortcut some of my work in my integral here. And again, if you don't notice it, that's okay. All right, so if I kind of just look at what I have here, though, since I did notice that, I'm going to notice that this part, this came from the x, and this came from the y. And so not that those functions are 0, but when I integrate over those terms, I'm going to get 0 for those integrals. So I really just have to end up integrating over this last part here that came from the z. So I don't want to forget my r, my limits of integration and everything, but I'm going to go ahead and rewrite this down here with just the part that I need to evaluate. All right, so I'm going to end up integrating the function zr. And we have that set up with z on the inner integral, and then r, and then theta. All right, so from here, it's just pretty straightforward integration. Maybe you do some algebra at some point. So integrate with respect to z, I get 1/2 rz squared. And that'll be evaluated from z equals r to z equals 6 minus r squared. And my outer limits of integration and differentials are still there. They don't disappear. I'm just working on this inner part here. All right, when I go ahead and evaluate that, I'll still have these outer limits of integration. And I'll go ahead and plug in. So these are going in for z. Remember, that was a z on my inner integral. So that last integration was with respect to z. So 1/2 r times 6 minus r squared, the quantity squared, and then minus 1/2 r times r squared. And I'll write down my differentials here just so I have good notation. Okay, so I want to simplify this. So I might kind of stare at this for a second and think about integrating this. I could do a u substitution on the first part and not have to expand it out. But if I do expand it out, I'll probably end up with some like terms that I can simplify. So I'm going to go ahead and do that. Just expand it out. Okay, so I do have some like terms there. Looks like I can go ahead and combine. Okay, so let's go ahead and do this next integration here. So I'm integrating with respect to r. All right, so I'm going to go ahead and put in my 2 and then my 0. All right, so 0 to 2 pi will just be 46/3 times 2 pi, or 92 pi over 3. In exact form. Okay, so while we could have set that integral up in rectangular coordinates, the actual integration ends up a lot easier if you convert to polar. All right, there's another example in the next video.